All right, so welcome back. We're doing this maximum likelihood business, but before that, I mentioned a couple things. I noticed, okay, there's been some people that have come. So first point is this guy. There's some people that have asked me about previous versions of lecture notes, which I had some I guess mistakes and types of things, which has confused people. So yeah, my recommendation is try to use the latest version of lecture notes. I know this is kind of annoying and not always so easy and possible, but yeah, like if you're confused about something and you refer to the course notes and it's different than in the lecture notes, it's probably the case that the lecture notes are old and incorrect in some way. So just a heads up. Other thing I wanted to mention, okay, so I'm just gonna go back to the last bit of the last lecture, which was on this evaluating models with regularization business. And I want to talk about this index K versus J, because yeah, this might get a little bit confusing because I did it a little bit differently in the written up course notes. Okay, so let me quickly review this. So in this stuff for evaluating models, there was this regularization business, and we had a new estimated loss function. Okay. And in this new estimated loss function, we had to, we tried to minimize it because that was our goal, to find the minimizer. And so what we did is we took the derivative and set it to 0. So in particular, we wanted this oh, sorry, we didn't set it to 0. What we did is we took the gradient, and then we were going to do gradient descent with it. And so what we needed was this gradient term. And when you calculate the gradient, you need these partial derivatives. And I just wanted to point out something about indexing that might confuse people. So I originally had j's here. But now I write this with k's. And the only reason I write this with k's is just not to screw up indices. And what I mean by that is this new regularization term already is using the index j for summing over all of the weight indices. Okay, so it's already using j here. So to be technically correct, you should be using a separate index when talking about the derivative index here. The reason why is because when we take the derivative of this g function, which is the regularization thing, what you'll find is that, yeah, you're trying to take the derivative of this g function, and if you want to take it for the kth index. And so that actually makes sense because now here you have some indices from j to 1 to whatever, and then the kth thing would pick out when k equals j, then you would pick out that w. If on the other hand, you would be taking with respect to j, that doesn't really make sense because j here is referring to every single index. So anyways, this is a technical detail. So to be mathematically correct, you should really be using different index k. So I've just been using k here instead of j. And that's how it's written in the course notes too. Okay, that's all I want to say about that. Then if we go back to what else did I want to say? Yeah, I'm just going to, okay, one more thing about terminology. So I was saying that, and this leads us straight into the lecture about the maximum likelihood stuff. Okay, so there's this, we're talking about maximum likelihood estimation. And we said, okay, instead of estimating the loss, the expected loss, and then minimizing that over predictors, why don't we do a different approach, which is observe that the best possible predictor is f base. And f base, if you write out this thing explicitly and actually calculate the argmin with the integrals and so on and expand this expectation, you would find this, which if you expand out, you find that it has this formula. And so then we say, why don't we just, and here's what the note was saying, why don't we estimate this? I said approximate before, and I'm just going to use this word estimate here. Instead of approximate, I've just changed this. And this is more to line up with the fact that it's called maximum likelihood estimation, and it's because you really are estimating this PDF or PMF term. Okay, so that's why it's just to line up with the the naming of maximum likelihood estimation. Okay, so I said our goal is we don't know this, but if we did know this, then we would just calculate this integral and we would get f base. Okay, but we don't know it, so what we're going to do is we're going to estimate this guy using this thing called maximum likelihood estimation. And then once we have it, we're going to plug that in and see what we get for our estimate of f base. And I think you'll be quite, perhaps it'll be quite a coincidence what we get. But anyways, we'll get there at the end of today's lecture. Okay, so then we needed some basics or background on maximum likelihood estimation to get started. And once we build up our background and understanding of how to do it, we just apply it to our case and see what happens. Okay, so what was the story here? The story was that you have this data set, already matches kind of our setting of these random variables, and they're all IID. And for this reason, okay, and they have some distribution and stuff. And each one of these random variables themselves have a distribution and a corresponding PMF or PDF. Okay. After that, can you guys hear this like background noise? I don't know. There's some like people cutting things outside. If you do, please send a message in the chat and I'll try to like do something about it maybe. Okay, anyways, back to business. So there's this data set, has random variables. Each random variable is independent and identically distributed, which means every single one of them has the same distribution, which also means they have the same PMF or PDF. Okay, cool. So that was the state. And then what we found is that, like, how are we going to estimate every one of these PMFs and PDFs? Like, how do we do this? And maybe the story is better seen through the fact that, okay, there is some true PMF or PDF of all the data, right? That's what this thing is. That's the true one. And if you plug in the data set, you would just get this equation. And then you would notice, okay, because of things being independent, I can actually write this thing as this product of the corresponding like individual random variables as PMFs and PDFs. So you get like some nice new representation. And then since they're identically distributed, you actually find that you can write it as the exact same PMF or PDF, this P of Z. And that gives you this really nice like compressed representation of what the probability of the actual data you saw is. Okay, so the point we're at right now is like you got some data, and for the true PMF or PDF, it has like some kind of like probability, or we're going to call this the likelihood of occurring. So that data has some likelihood of occurring. Okay, and that is actually described by exactly this formula. Notice that it really only depends on P of Z, and our goal is to find P of Z. Okay, so the approach of maximum likelihood is to say that, okay, I don't know what P of Z is, and for different P of Zs, there's different like likelihoods of that data that I got occurring, right? So I have some data, and there's like some different likelihood depending on my P of Z. And since I don't know what P of Z is, my best guess, my best kind of estimate at it is just going to be to pick the P of Z that makes the data I saw the most likely. So in particular, we're going to say, since we don't know P of Z, and we know that this thing describes the likelihood, okay, of the data we saw occurring, we're going to pick our estimate of P of Z to be this thing called P MLE, and it's going to be the P that makes this thing, which is exactly saying we're going to pick the thing that makes the data the most likely. Okay. And I show a little plot explaining this in a second. Okay, so then we saw some examples. So we're going to do the discrete case first, and then we're going to do the continuous case after, and then we'll apply everything to our setting. Okay, so the first case was the discrete one. So like you have some data, and it comes from like coin flips. And you don't know what the parameter, the unfairness kind of like parameter of your coin flips is, but you know it's a coin flip, so it's a Bernoulli. So you know that this PMF or PDF has this special form. And so what you're going to do is you're going to search over all of these guys. So that just means like pick the best P, the argmax P from this function class H, and that function class just has PMFs of exactly the Bernoulli form for all possible parameters alpha. And you're trying to search over alpha. So then we had this nice trickery, or like, I guess it's not really trickery, just like a nice way to think about optimizing functions, is that if you make if you parameterize the function, meaning that you can describe the functions in your function class through a parameter, in this case alpha, then searching through functions is the same thing as searching through the parameters, because every function can be described by a corresponding parameter, right? So like, for instance, this is a function in the function class, and it's entirely described by this parameter alpha. So I can just say that PMLE, which is our PMF that maximizes the likelihood of seeing the data, right? Because we have some, like we actually did flip like n coins. So this thing is equivalent to P of alpha MLE, where this alpha MLE is described by this process of maximizing the likelihood, but now where this like PMF is described by an alpha term. Okay, so this allows us to actually like properly solve the optimization problem, because now we're searching over just a parameter instead of functions, and we know how to deal with this kind of stuff. Okay, so that was the case we got to. So we're like this kind of summarizes. We have this PMLE, which we're going to solve for. So this is just a mathematical, like exactly an optimization problem to solve for PMLE, which is through this alpha. And our hope is that this is an approximation to P of Z, and it's a good one. Okay. And then there is some terminology that's pretty important, which is that you call this thing the likelihood. It's just called the likelihood, but it's really like the likelihood of your data. And then there's also this notation, which is instead of writing the alpha in the subscript to say like this is the parameter the function is based on, people like to write that it's conditioned on the parameter. It's like the likelihood for that parameter. But this is a little bit of an abusive notation because alpha here is not really a random variable at all. It's just like your parameter. Okay, now the new stuff is first, we're going to get, okay, so we're not actually going to solve this for the case of Bernoulli's. And the reason why is because I think you're going to solve it in your assignment, if I recall. And also, this is going to be what we need for classification. So I just leave it kind of for later on. But what we're going to do is we're going to then go over an example for when the random variable is continuous, and we will actually work out how to solve this. Because that applies to the setting of the regression setting. Okay. So I leave this here, but you can imagine all you do is just like take the derivative and set it to 0, and it turns out to work more or less. Okay, so but first I want to give you like an example of interpreting what it means to pick the most likely PMF. Okay. So recall that we have data, right? And let's suppose that that data, we have 5 samples of this coin flip. So how do we like think about this? One way to think about this is on the x-axis. So this x-axis I think of as the corresponding outcomes of a coin flip. So the coin can either be 0 being heads or tails, or 1 being heads. And I get these coin flips. So I need 5 coin flips. So let's create 5 coin flips. So perhaps on the first coin flip I get a 0. On the second coin flip I get a 1. Then I get another 0. Then maybe I get one more 0. And these are just like x's all overlaid on 0. So it means I got 3 zeros so far. And then I got maybe one more 1. So this is my data set of 5 samples. So I've got this data. And now I want to ask, so this is like, I want to ask, what is the underlying PMF, which also tells me what the distribution is. Like, what is the underlying PMF that generated this data, right? So each coin flip is getting sampled from some distribution. But I don't know what that distribution is. Like, I don't know what the alpha is for it. So some options are like, if the alpha was 1, then I would have definitely seen 5 heads, right? If alpha is 1, that means 100% of the time you get heads. So like, just like really intuitively, it's obviously not 1. Alpha is definitely also not 0, because if it was 0, then with 100% probability, I always see tails. Okay, so it's somewhere in the middle. And maximum likelihood allows us to exactly like, well, it gives us a way to pick an alpha. And how would it pick it? Well, it's going to pick it through saying, exactly, I want the alpha that makes this thing multiplied 5, like in this case, this P alpha of the corresponding things multiplied 5 times to be the smallest. Okay, and if you solve and get whatever, you're going to get what that is. But first, I give you like some intuition for what you would expect. Well, you probably think that okay. So first of all, what we do know, right, is that alpha is actually the probability, or okay, it's the PMF. Oops, the PMF at 0. PMF at 0 is 1 minus alpha, and then PMF at 1 is alpha. So we know that these two added together are actually 1. Also for PMFs, this is actually exactly the same as the probability of getting 0. So if we saw 3 tails, it's probably more likely, right, that that the alpha like is somehow weighted towards tails. So maybe you would expect to see something like this. So like if this is alpha, then this would be like 1 minus alpha. And so you might see that, okay, this might be something like what your MLE estimate would give you. Something like this. And so really what's going on is that the maximum likelihood thing is searching over all possible choices of alpha. So like another choice would have been maybe like this and this. But this is probably a worse choice because like it's probably not likely this is where the data came from, because we'd expect maybe all zeros there or something like this. So Emily will pick something like this black thing, these black points here. Okay, and it actually turns out, and we'll, I guess, yeah, maybe I don't tell you the answer because I think you solved for this in the assignment or something. But anyways, it's going to turn out to be something. I don't give it to you, but that's what Emily is solving for. It's trying to pick exactly what like this alpha point is, and that gives you 1 minus alpha. So yeah, okay. I don't know if there's any questions about that, but there is. Yeah, please ask. That's one interpretation for the discrete case. You're really just trying to find the underlying kind of like the distribution that's giving the data, and the way you do this is by just picking the distribution, or the PMF in this case, that makes that data the most likely. That should make a lot of sense, hopefully. Okay, so let's see, what does that mean? What does that mean with densities? Because now we're in the continuous case for this example. So let's try it with densities. Okay. Yeah, okay, this is the version I thought. So continuous case, why is it continuous? Well, let's say we are getting samples of people's height. Turns out that people's height, for some reason, does follow a normal distribution, more or less. So we say, okay, like this is kind of an assumption we're making, which is that the data, Zi, like each of our samples, is coming from a normal distribution. Okay, and we assume that for some reason, the variance is always 1. This is really just like a simplifying assumption to make the math work out easier. But for this example, we're going to, for some reason, assume that the variance is 1. And then there's some true mean parameter. So this is like the kind of the average height, but we don't know what that is. Okay, and since we assume this, that means that the PDF of our random variables follows this normal distribution PDF. Okay, this is just like already you've seen this before. It's given to you. And the thing is, there's some true mu star. This is like the true average height of people. We don't know what it is. And so what we're going to try to do with axiom likelihood is really learn what is mu star, or get an estimate to it. So how do we do this? Well, what we do is we say, okay, our function class of PDFs is the set of all PDFs that look like normal distributions PDFs. Makes sense. And we consider all parameters mu. So then to solve for the PDF that maximizes the likelihood, you solve for the mu parameter, and then you solve for this mu parameter. Okay, and that should be a good estimate of the true PDF. This is the true PDF. Okay, how do you do that? You search over these parameters mu in the sense that you maximize this likelihood thing. Okay, so you're trying to maximize this likelihood as before, but now over parameters mu. And here I'm using the notation you've seen that I said is sometimes used, where you're like conditioning on this mu parameter. So this mu would change the corresponding function here. And maybe to make this more clear, like this is like what the mu would be here. Okay, and yeah, and each one of these, that's what I was saying here. So each one of these guys is an element of the function class. And this dot notation just means like all possible inputs. Okay. Hopefully that makes sense, like problem setup. And so for this case, we're actually going to solve this optimization problem. Like all that's left, right, is to just find what is this mu MLE. And that turns out to just be like an optimization problem, and you take some derivative, set it to 0. So that's what we're going to do. But before that, I give you the interpretation again, but with for the densities. So we're trying to pick the density that maximizes this expression. We call this thing the likelihood. And you can think of it as you're trying to pick the density that makes the data the most likely, or like that, like you're trying to pick the density that for the given data you have has the most density in those regions. So what you can think of is, in this case, I have way more samples. I don't know how many I quite have here, but like these are all these red dots. Perhaps there's like 12 or something. It's not 4, or it's not 5 anymore. So these are all of my samples, right? These are just values of people's heights. So this person is like maybe 50 centimeters. I don't know if that's very short. And then maybe this is like 2.5 meters, and maybe this is like some average at like 1.7 meters or something. So yeah, you can see on average people are like maybe around this 1.7 meter height or whatever. And now you're trying to pick the density that makes this data the most likely, right? And that makes sense. Densities take in individual points, these ZIs, people's heights. So like visually, you can think of what's happening is that you're taking this distribution, okay, you're taking this normal distribution, and you're trying to find the parameter mu. And mu describes the mean of the normal distribution. So you can think about it as you're really like testing all possible normal distributions, and you're just like going through all of them, and then eventually like you're going through, you sweep through all of them, and for each one, what you're doing is you're calculating this corresponding equation, which is you plug in every single data point into the normal distribution, multiply them together, and you get the probability of seeing all of the data you saw. And some distributions will have that as being larger and smaller, and you want to pick the one that makes it the largest. So once again, you could really think about taking this normal distribution, sweeping over all possible parameters of mu, and picking the one that makes the most likely. And what you will find is that it will look something like this. Okay, should make sense. It's really centered. Most of the density is centered around where most of the points are. Okay, and now let's solve what the actual equation of this thing is. I've just been giving you all these intuitions. Let's solve what it is. So how are we going to do that? Well, we're just going to take the derivative of this thing and set it to 0. And it turns out that there's some tricks you want to do that make taking the derivative and setting it to 0 a little bit easier. In particular, if you just try to do it directly, imagine trying to take the derivative of this. with respect to mu. So like what that would mean is you'd plug it in, you'd plug in the definition of this thing, which would be an equation of this type. And now you need to multiply this equation n times and then take the derivative. That would be like n applications of the product rule. And you can do it, but it's just like really messy. So usually if you have n multiples of something that depends on the same value over and over again, it's really annoying to take its derivative. Okay, so this is kind of the important thing to know, is that what people do is instead of maximizing this, they maximize something else. And this something else has the exact same maximum, like minimizer point, or sorry, maximizer point. So the mu star, or the mu that achieves this argmax would be the same. However, now we're going to change the function. So we're not going to maximize this guy, but we're going to maximize its logarithm. Okay. So this is, oh, let me do this with one extra step so I don't jump too far. We want to maximize this whole thing. Turns out maximizing that is complicated, like mathematically, just working it out. You could do it, but it's just annoying mathematically. So what we're going to do is we're going to take this log, and we're going to see why we took the log and why it's mathematically nice and stuff in a second. But what you should notice is that these are equal. Why are they equal? And they're equal because the logarithmic function is the thing called its monotone, basically. And what that basically means is if you had a function and you apply the logarithm, the order of all the points stays the same. Okay, so that would mean that also the maximizer, the mu that achieves this maximum, stays the same of this function. Okay, so that's just like an important thing of logs. I don't want to get into any more detail about that. Okay, but why do this to begin with? Well, the reason to do this is because then what we can do is we can take this and we can remember a logarithmic property. Okay, what's the log property? Okay, one other thing to note. Throughout, whenever I use log, I really mean log base e, which oftentimes you'll just see written as natural logarithm ln, but I'm going to use just log throughout. This means log base e. Okay, one note. Second note is that I'm going to, so far I haven't simplified this, but how am I going to simplify it? Well, I'm going to simplify it by using this property, which is that log of two things multiplied by each other, AB, is equal to log A plus log B. Okay, so here we have n things multiplied to each other, and you can apply the same property. So the way we do this is we take out the product, we move the log inside, and now the product, it's no longer a product, but it's a sum, right? Product becomes sum here. Okay, that's that step. Okay, and then at this point, we're almost like this actually turns out to be a really easy thing to optimize. But before that, we do one more thing, and it's purely for convention. And this is, people don't like maximizing things, they like minimizing. And like, okay, it's not really, it's just like all of optimization literature talks about minimizing things, and as we've seen, we've always been talking about minimizing. So people like to talk about minimizing things. So we're going to make this a minimization problem. How do we do that? You might recall that the arg max of something is equal to the arg min of minus that thing. So we change arg max to arg min. Great. Okay. So now at this point, we really just do take the derivative and set it to 0. And before doing that, I address one question, which is, once again, why don't I just write log n? The reason I don't, or ln, like this natural logarithm, is entirely because it's very common in all of literature to just use log and always assume that it's actually this. And I am almost certain I'm going to forget to write ln everywhere. So it's purely for me to not confuse you guys by just flipping these around all the time. So I'm just going to write log, because even at this point, I almost completely forgot to mention this. So I'm just so used to writing log all the time. So otherwise, yeah, there's going to be a problem that the course notes are just not going to match up in random places, because I just can't remember to write this everywhere. So yes, log is just always means this in this course. You're not going to need this base 10 thing anywhere else. So that's the reason. Yeah, but if I believed myself enough, I would just write natural logarithm. Okay, and the change for product to summation is entirely because of this property. Here we have the logarithm of a product, A times B. And now here we have the logarithm of A plus, which is a sum, log B, right? So, and to map here, log of the product becomes the sum of the logs, Okay, great. And I wanted to mention that this thing now has a very intuitive name. It's not the likelihood anymore. It's now called the negative log likelihood. And okay, that's it. That's all I want to say. And now, shall we continue with the actually taking the derivative? Okay, so how do we do that? What we do is we take this, and we actually plug in the expression, right? We need to know what we're taking the derivative of. So let's plug in the expression for this p of z guy, and we know what that is. It has this form. So let's take that form and pop it in there. And this turns out to be a very nice form. Okay, so before doing that, I'm going to use once again this property that the log of the product of two things, so that's here we have this thing times that, is the sum of the logs. So that means I can take this guy. And here you can see why log is going to be, again, very nice for this case. Which is I can write this log as now the sum of logs. Okay, and this sum is over everything. Okay, great. So you have this expression. Okay, so I'm going to do, I guess, 2 steps here just to save a little bit of time. And okay, let me finish this and then I'll answer some of the questions. And so notice how you can write this argmin as really like you have this term, and then you have the sum applied to this term. So I could just split the sum across the two of them, but here I wrote it with bigger brackets. But what you want to notice is that you're minimizing over mu, but this term has nothing to do with mu. It's a constant number. If I add a constant to a function, it's not going to change the minimizer, right? So like the argmin of a parabola that's shifted up and down is not going to change the x value that minimizes it. So what I can do is I completely remove not the sum, but like this term inside the sum. Okay, so that's the first thing to notice. The second thing to notice is here I'm taking the logarithm of the exponential. And if you remember, the logarithm of an exponential is exactly just the inner thing. Why? It's because like the logarithm is asking e to what power gives me this thing. And here this is e to the power of something. So like e to what power? Well, exactly this power. So okay. So that allows me to simplify this quite a lot. And what we do is we get to here, remove this guy. Don't need that anymore. And we don't need the log. We don't need the e to the power of things. And we do need the minus. And so we get to here, right? And then the minuses cancel out. So I also remove that. And so we get a very nice looking expression, right? Yeah, so this is great. So that's what we need to find the, okay, so far I haven't taken any derivatives, right? All I've done is I've simplified the function. And so now all that's left is to take, so how do we find the argmin of this guy? We take a derivative and set it to 0. And that's super easy to do now because this function's quite nice. So what we do is we call this guy g of mu. It's a function of mu. And what's left to do is just take its derivative and set it to 0. So let's just finish that. So dg d mu, and it's a function of mu. What does that become? Well, I do this quickly again. The derivative of a function like this is, once again, it's equal to the sum of the derivative of each term. And what's the derivative of each term? Well, it would just be 2 times the inside thing. And then the derivative, okay, and then the derivative of the inside has a minus 1, because the derivative of minus mu is just minus 1. So I kind of do these things quickly now. Okay, so all that put together will give us, the 2 comes out to the front, and it's divided by the original 2, and then there's the minus, and then we have the sum. Oh, we don't need the division. And obviously this just simplifies to minus I equal 1 to n of z. Oh, let me fix one thing in a second here, which is I forgot to index I here. Like, what is this I talking about? It's all about zi, right? These are all talking about zi. So I just copy and pasted this completely from, yeah. So that's what the I is over. It's over the data, zi's. And yeah, so that thing. And then to finish, we need to set this thing, right? We need to take the derivative, set it to 0. So let's solve. So the way to solve this is, I guess I write out all the steps for this, which is, there's only 2 here. I expand this guy. Looks like zi. And then I take the sum into the next thing, which would become minus minus. And then I get sum I equal 1 to n of mu. And notice how mu doesn't depend on I, so this thing is really just n times mu. This thing's equal to 0. And so what I do is I take this thing to the right-hand side to make it positive, replace this sum with n, and I get to n times mu is equal to the sum I equal 1 to n of zi. And finally, solving for mu, I get that mu equals 2, and this is a really familiar, or like a really pleasant formula of what you would expect, which is it's the sample mean of your data. And what is this thing? This is the mean of your normal distribution. So this is telling us that if you want to find the normal distribution, or like the PDF of a normal distribution, that makes the data the most likely, what you should do is if the only thing you don't know is the parameter mu, right? The only thing you don't know is this guy. It's the mean. This is actually the mean of it. What should you use for your estimate? Well, it tells us that our estimate, the one that makes the data the most likely, is just picking mu to be the sample mean, right? This is your samples. You have n samples. You sum them up, and then you take their average. So this is really nice, intuitive. I think it makes sense. And what that would mean is what you would do is you would take all of these samples here. You would sum them up, divide by n, and you would get a number, which is this thing. And that would be the center of your distribution. And then you get this PDF code. Okay. So that really concludes this example, and that's the whole process of calculating the maximum likelihood estimate. And here the estimate is of the parameter mu. And once you have mu MLE, we just solved this. We have mu MLE. We now plug it into this thing, which just means plug it into here. And now you have an expression for what the PDF of the normal distribution that maximizes the data is, the likelihood of the data. Okay, now I answer some of the questions before. Next step is just to apply this to our setting. That's all that's left to do, and see what we get. Okay, so there's quite a few questions actually. So someone asked, why is it negative again? And the reason it's negative is purely for convention of what people like to do in optimization theory. And if you did the argmax, you would get the same result you find. If you just took the derivative of this and set to 0, you'd get the same result. But people in optimization theory love talking about minimizing things. You've seen that we've studied everything in optimization about minimizing things. And then there's some like results you get, which we didn't talk about in this class, but like that talk about like the minimum of things. But even this like idea of like things look like a bowl shape, it looks like a bowl because we're always talking about minimums of things. So you find the minimum of the bowl. If we talked about maxes, then you would have to flip the bowl. So then it looks like I don't know, like a union symbol. So yeah, purely for convention. About people love minimizing in optimization theory. How to get rid of the log 1 over 2 pi? Yeah, so this is good. We're just basically re-clarifying some of the steps. So we got rid of this thing. And the reason we got rid of it is because we're trying to find the parameter mu that maximizes this expression. But notice that this thing doesn't depend on mu at all. And if you shift a function by a constant, that's what this is, shifting it by a constant, independent of the parameter, you don't change the maximizer of the function. And the quick plot for this is if you plot something, for instance, a parabola, if you shift, so I guess the important thing is that this is the minimizer of it. Well, really, it's not, that's the minimizer, that's the x value. So this is the minimizer here. If you take that parabola and you shift it up and down, that's all that this constant is doing, the minimum doesn't change. So you can just remove that. So that's why we removed the log. Okay. Yeah, or you could think of if I kept it and took the derivative would become 0. That's like I just didn't want to keep this thing around for taking derivatives and stuff. And finally, yes, and so and answering another thing is like you're kind of going ahead of things, and this might be on the assignment or midterm or things like this to work out, which is we haven't discussed is what's going to be the case, and you could do this if you make this a parameter as well. Or maybe you let's say you set the mean to 0 and you made this a parameter, sigma squared, and you tried to solve for what sigma squared is using this approach. What would it be? And you find that it is also the sample variance. It's going to be like 1 over n times the difference squared. Yeah. So it's all very intuitive in some sense. Yeah. And the minimum, or sorry, did I say minimum? I meant I really should be saying the word minimizer. The argmin gives you the minimizer, the value input to the function that achieves the minimum value of the function, right? So you input this into your function, it outputs this minimum value, but the point, the minimizer, is always the same. Okay, so not the actual value of the function staying the same. Okay, so now we move on. And yeah, maybe I can. So it's still talking about the sample variance. The question, which is like, in the sample variance, do you get like this 1 over n or this 1 over n minus 1, where the I was being a little bit sloppy, which I think like sample variance is actually 1 over n minus 1, but here I think you do get 1 over n, so it's not exactly the same. So like it's what people, yeah, it has some like it's a slightly off because it just uses 1 over n, not this 1 over n minus 1 thing. And there's some reasons for that and stuff, but yeah. So okay, I leave it at that. Let's continue. So what's next is this is our goal, which is to find this thing, this PMF. Well, okay, we're doing regression, so everything is continuous random variables. So this is a PDF. So we want to find the PDF of y given x, or an estimate of it. And so I guess here I didn't change things, so I change it now, which is we're not approximating. This is to line up with the notation, is we're estimating the PDF P of y given x. So let's do it. And you're going to see that this is very similar to what we've been doing, except now instead of z's, we have these things. So instead of z, our z is really just a multivariate random variable, which is our feature label pairs. And there's going to be a slight detail about, okay, we see it right away. So you have a data set as before. Z's are now these things. These things are multivariate random variables. They are all IID as before, just like the Z's were. What I've done is I've changed this thing at the bottom with not Z, so I've plugged in this for Z. Okay. And so what we get is this, there's a PDF here, but it's the joint PDF of X and Y. And we almost have what we want. Like, okay, this so far everything here matches what we've been doing with MLE, but we want the conditional thing. Okay. And so to get the conditional thing, what we will find is that we work some things out, and you will see that it actually, if you just try to find this joint PDF that makes the data the most likely, then you will actually really only care about maximizing the parameters of this. And okay, let me just give some details, but what I want to highlight is so far this is not exactly the same as this, but our goal is really to find the estimate here. So how are we going to address this? Well, I just show you. Okay, let's do it. So I want to make one first observation, which is we're going to make. Okay, yeah, let's do this first. So I want to work with this. Okay, so I want to like find an estimate of this. So I'm going to need to search over these things somehow, and we're going to get to that in a second. But before, like, as I've been saying, like if you want to find like the minimizer of something, or like the argmax of things, you can't search over functions. So we're going to need to search over the parameters. So as we've done with the previous two cases, we're going to need to assume that this thing is coming from some special distribution that has a parameter to describe it. And here is where you really are assuming. You don't know what the distribution of y given x is. So in like without any extra knowledge, you really are as good as guessing. But a classic thing to assume is that it's normally distributed. And so this matches nicely with the previous case. So in here, really, it really is an assumption. And how reasonable this is I don't have too much to really say about that, to be honest. But this is very standard in exactly the regression setting. So when people actually say linear regression, a lot of the time they actually just like implicitly mean that this assumption is actually true. And so that is that the conditional distribution of y for a specific xi follows a normal distribution, but in a special way. It follows it in the fact that this parameter is dependent on what your x value is. And it's related in exactly this linear way here. Okay, and then this thing's still assumed to be 1. So this is actually like most of the time kind of actually assumed directly in the linear regression setting, which is that once again, the conditional distribution of y given x follows a normal distribution where the variance is fixed to 1, but the mean is a linear function of some parameter w and of x. So intuitively, like if your y's, if your labels are increasing as x increases, so maybe as the number of rooms increases, you expect y to increase. You see that through the mean here. So you would have like a linear equation that has an increasing slope. And so as the slope increases, this value increases, so the mean changes, but you would find that the variance just is always the same. So like, yeah. And okay, it's really hard to draw this plot. So I'll probably just draw it and kind of maybe, okay, yeah, it's really hard to kind of draw this plot. But like the way to think about it is like, if this is kind of like me drawing the mean, maybe the mean is following this trend. But then what we're saying is there's some like, the data is obviously like for a specific fixed point. There's multiple options for what you could see for data here. And we're saying that the distribution of the data you would see at this fixed point for every single fixed point is following a normal distribution. So if you kind of think about it, like kind of being sloppy here, but I could draw the density at exactly this point, and this would be like a normal density. So there's like a lot of probability of getting points around here, but like much less as further out. And so for each x, you could really think about drawing these kind of like normal distribution or normal densities, which is also, once again, kind of sloppy because they're just densities, not distributions. But they really do give you this knowledge of like, it's more likely to see data around this and much less likely out. And the mean of all these is changing as we move along. Okay, so that's really how this x depends on this. Okay, so kind of, this is standard assumption a lot of the time, but I think it's worth talking about where it kind of comes from, or like what it implies. Okay, after you get that part, what is going to be, okay, why is that useful? That's useful because we're going to want to find this thing that maximizes the likelihood in a second. And the reason it's useful is that then I can write this py of x in this really nice explicit form as we've seen before, which is as follows. So okay, I'm going to just copy this. Okay, even better. I'm going to copy exactly this. So like this is the assumption we had here, right? Which is that the data came from some normal density with some true mu star. So we're going to really just copy and paste this kind of thing. So it gives us this information, which is that now not p of z, but p of this like x, y, z thing, right? So p of y conditioned on x of y conditioned on x. And I should really write one more thing, little x. Okay, so for this little x, this conditional PDF is now equal to not mu star in here. So I should delete this guy. But it's equal to the new mean of things. So what's the new mean? The new mean is this x that we've conditioned on times w, and this will be w star. This will be like the true parameter. Okay, so now what we can do is we can search over these parameters w star. And so I'm not going to write the function class and stuff like this to save some time, and like you can understand what it's going to be. So like each one of these PDFs is described by some parameter w, and the true parameter is this parameter called w star. And our search is really, or like this maximizing the likelihood, is trying to find the parameter that makes this thing the most. Okay, that's going to make the likelihood function the largest, but that's trying to find this parameter that's really close to w star. Okay, so how is that the case when we still haven't addressed this problem with this joint thing? Okay, so for this, I give you a property first, or like this thing that we can use the what was it, the product rule for probability density functions as follows. So you might remember that if you have something like this, if you have the joint PDF, you can rewrite the joint PDF as the conditional. This would be y conditioned on x given to little x of what? Of y given x times the marginal. Okay, maybe I'm going to stop writing these subscripts to really save on time and space and confusion. So you know, like this is abusing the notation, but it's the abuse that we've talked about before, which is that you don't write these subscripts and you know just from the inputs what I mean. So this is really the marginal PDF. This is the conditional PDF, just from the context. Okay, so this is just the product rule, as you've seen many times used before, hopefully. And so we're going to go and just use maximum likelihood approach and everything and pretend like we're trying to find this thing. And what we will find is that this term is actually unimportant to us entirely. And okay, why is it going to be unimportant? It's going to be unimportant as long as we make no assumption on how it's distributed. So like outside of knowledge of like what its distribution is and stuff, and if we don't make any assumptions similar to this for this marginal distribution, what we're going to find is that if you want to maximize this, it's the same as just maximizing this part. And this part will be irrelevant to us. And so then, yeah, it turns out that you can really find what this is by just finding what this is, by not making any assumption on this. So let's work through it and then find how this works. But yeah, this is going to be how we end up basically solving for this through using this. And you could obviously make assumptions about this, and then it would change things. But the standard thing, yeah, like outside of extra knowledge, you just don't know what that is. Okay, so let's do it. So what does that look like? And what that looks like is, okay. Let me just take this to make it very clear. So we start from exactly the same point. We want to calculate okay, so what are we doing? We're calculating now W MLE. And this thing is also a vector, so that you might think that makes things a little bit more complicated. We're going to find that it's really not a problem. Okay, so this is our actual setting now. Okay, so let's solve this problem with the correct terms here. This thing now is y. How do I usually? I guess I write x, I, y, I, w. Okay, we're not searching over mu, we're searching over w in R of d plus 1. Okay, so this should hopefully make sense. All I've done is taken the previous example and changed what the parameter is and our random variable from z to being these xy pairs now. Okay, let's solve it. And guess what we're going to do? We're going to do the exact same steps as before. So I'm not going to explain as much details. So I start with this, and then what I do is I apply the logarithm. And I'm going to apply the logarithm and the negative at the same time. Argmin, or the negative log. Then I'm going to pop the logarithm inside the product and change the product to a sum. Erase this. Okay, maybe what I should do is also put brackets so there's no confusions. This logarithm is applied to everything here. Then I take the logarithm, move it inside. Now it's applied to individuals. And you have a sum outside. Okay. Now, what we're going to want to do is we're going to want to make use of the product rule here. Again. Or sorry, not again. We're going to want to use the product rule to expand this. We have done that above. I just reminded you of this. We're going to use that. So that will imply that we no longer have this type of thing. We have here now the conditional of yi conditioned on xi vector, comma w. Okay, so we've added this w to imply that this is like based on some parameter w. And now notice how this thing here is p of x, I, but it has no dependence on w, so I remove it. Okay, so there's nothing to do with w. W only really told us about this conditional thing. And in some and then how is it here? Well, it was here through this kind of dependence here. So it obviously, because this w influenced the conditional, it obviously would influence the joint in some complicated way, so I wrote it here. But in reality, yeah, so this is what we've seen. We know that the conditional depends on this parameter w. It tells you how the normal distribution, its mean looks. The marginal, we made no assumption, so I don't write anything about the parameter w here. Okay, so this is an important part to understand because what I do next will show you why this marginal doesn't matter. So I use the properties of logarithms again, which is that the logarithm of this thing times another term is equal to the sum of the logarithm of each. In this way. Okay, if we want to keep the negative here, and I didn't want to keep it there, I'm going to move the negative outside to not make it look so ugly. All I've done is taken the negative out, right? That's okay. So now I can use plus here. Okay, so I just use the properties of logarithms. And the important thing is the sum is still applied over everything. Okay, the great thing about what's happening now and whatnot is that, okay, notice again that we're optimizing over W, right? So what does that mean? Well, that means that, okay, this term is depending on W, but this term doesn't depend on W. It's independent of W because this thing has nothing to do with this parameter. So this turns out to be quite beautiful because now the argument is once again not going to be affected by this term. So if I move a W, if I move this function, if I scale it by a constant just like before, the argument isn't going to change. So I can just remove this term entirely. It's exactly like the way we could remove this term here. It has no dependence on the term, so it's just shifting the function up and down. Okay, that kind of addresses the fact of why you could just talk about the conditional, or you can only make if you just make an assumption on this conditional guy, then if you try to maximize the likelihood in the way we've been seeing of the joint, then you just get back to solving for this parameter. Okay. Yeah, so let's continue. And maybe let me say one more interpretation in a second after I remove this term. So this guy's gone. We don't really need this bracket anymore either. Okay, so what we've got to is that all we've done is we've said that this expression in here, when you're talking about the minimum, is the same thing as what this expression was over here. Like, well, this whole thing together. So it turns out you can think about minimizing or like maximizing this guy as the same thing as minimizing this thing, but only of the conditional. Okay. So now this gives us a way to like calculate this. Like we're gonna once we solve this, we find W, and once we find the W, we have an equation for the maximum likelihood estimate of our conditional PDF. And if we have a maximum likelihood estimate of the conditional PDF, we're going to be able to use that to calculate F Bayes, and we're going to do that. So let's calculate this. Okay, so then the process is as we've kind of seen before. We're going to take this and we're going to plug in the definition of the conditional PDF. That definition was a little bit long again. It's that exponential thing, and we apply almost the same steps, but with a new mean. So let's go back and to make this, yeah, just so you can like really see the similarity, right? So we're just taking this and we're going to put it in here. But the only difference is we're not using mu here. Oh. I think no. Actually, we're okay. Okay, good. Okay, let me fix something. So what's Z here? There's no Z here, right? Like, what's going on? So here you might remember the Z is the random variable, and the random variable here is Y. And for each X, the mean changes. So this part was all fine, but the Z here should be Y. So yeah, so remember this Y here is the random variable. It's changing for each one of the X's. So that's representing the Z here. Okay, so what I really want is this guy, and I want to plug it in here. So let's remove what I had. Even though it's the same, I just don't want to like replace the Z's and rewrite everything here. So this is what we have, but we don't know W star. So I remove the W star. I'm just searching over W's. So I'm searching over W's. Ideally, I find W star, and this is how I approach it. Okay, so let us solve this. So first step I'm going to do is once again use the property of logs. I have a product of two things. I can now write as the sum. So I take it, and I write it as the sum inside here. Oh, I need that. And then that's all summed up together. Okay, then same story. This thing doesn't affect the minimizer. So I can remove this. Log and exponential go in. So then I can remove that. So let's do that step again. So I can remove all of this and this and this. And I can move it all in again. So this is just repeating everything you've seen before. And I remove this minus, I remove this minus. Oh, whoops. And I don't need all of these brackets. All right. So unsurprisingly, you get almost the exact same thing we've seen before, except now not mu, you have this linear thing, right? Okay. So now we want to solve this problem. But we have like, oh, one thing is that you need a transpose here, of course, right? This is it's a linear function of these things. So have I missed it ever or no? Okay. I need the transpose. Okay. So you might recognize this expression. What is going on here? We need to find the argument parameter for something that looks like the sum of things, where the thing in here, right, is like y, oh, other things. It's yi minus xi. You can think of this as like your predictor, your linear function that the predictor is using, trying to predict y, right? Trying to minus the square. Does this thing not, like, okay, this thing looks like the squared loss, or it should look familiar to you to the squared loss, right? They're just like, okay, there's a constant of 1 over 2 in front that doesn't really do anything, and you're missing an n in the front, but that also doesn't change anything. That's a constant. So what I point out, I say this, sorry, you're missing a 1 over n out front, but this really looks exactly the same as minimizing the estimated loss that we were doing before. Okay, so I wanted to, what was I going to do? I was going to do, okay. Anyways, so yeah, so instead of solving this complicated thing all over again for w, we can just reuse the solution we had before. Okay. What does that mean? Yeah, the one thing I wanted to mention, maybe I do this, is to make this really look the same as what we've seen before. Note that obviously, since things are squared, I can write it in this order, which is the order we've been seeing before, which is this is your linear predictor minus yi squared. So then it really looks like what we've seen before. And in particular, this whole thing, in that case, is now the same thing as L hat of W. This is the same thing, except since we aren't multiplying by 1 over n here, and this L hat has this 1 over n factor in front, if we multiply L hat by n, the 1 over n goes away. And since we need this 2, we would need to do this. So this is equal to this. But notice that the argument of this is the same thing as the argument of this. There's no difference of those two things. So what we end up getting is that the solution to this is just the solution we've always seen before, which is this A inverse B thing. And I'm not going to write out the definitions of what A and B are. This is the exact same thing as we've seen from the linear regression case and everything like that. Okay, so this is beautiful. We got to this point where like we can just reuse this previous solution. We got to here. Okay, we're making some. So what does this tell us? It told us that my W MLE thing, my parameter, is equal to the solution that we've seen before, and this was like the same. This is our W hat before, right? Okay, so at this, okay, so we got something that's saying that like the maximum likelihood estimate of the parameter is the same as W hat. But there's something a little bit weird. Or like there's something that still doesn't perfectly match, but we will make it match in a second, which is that this thing was the parameter of our predictor. This is the thing that's predicting the y values. But this thing right here for us, W MLE vector, what is it? What was the term? It's the mean of a normal distribution. So like, how are like, okay, we found the mean of our normal distribution. What does that tell us? Like, how are we making predictions? Like what was the whole goal of this whole exercise? Let me just, I know what I want to say next, but let me just double check if I missed anything up to this point first. Okay, I don't think so. But okay, so what are we gonna do? Like, we got this thing finally. Like, how are we using this to solve our original goal? So to do that, we should remind ourselves what our original goal is, which is the beginning of this whole lecture. And it was to find f bays. And the way we were going to do that is we were going to get an estimate of this and solve the integral. So why don't we do that? So we go here. Okay, so we need an estimate of this integral. So I claim now we have an estimate of this. So this is going to be approximately equal to the integral, everything's the same. But now we need to plug in our estimate. And so, yeah. So what is our estimate? So our estimate is PMLE. That's going to be our estimate. This is this conditional PDF. What is it? Well, this thing is just P of y given x with W MLE, right? And like, what is this conditional distribution? Well, that's, okay, I guess I read it again. 1 over square root 2 pi. This is just the definition of the conditional PDF with the actual parameters plugged in. Exponential of minus yi minus xi transpose. And now here we plug in W MLE all squared over 2 there. Great. Okay, so what, yeah. So and the claim is that this thing is approximately equal to the true conditional distribution for the corresponding little x value of y given x. Okay, so like that's the story. Yeah, so that's what we're gonna plug in. So let us go ahead and do that. Okay. Excellent. So that's where we got there. So like what does this whole thing tell us? Well, you might notice that, okay, you can kind of like look backwards. So here we had an conditional expectation, and we noticed that the conditional expectation, if you write it out explicitly, it's written as the values of the random variable can take on integrated over the integrals over the values the random variable can take multiplied by some conditional PDF. Okay, so now all that's changed is we have a different conditional PDF, right? So you can think about this as having a different random variable, y prime, where the y prime doesn't follow this distribution, the way this like y did, but y prime conditioned on x follows a different distribution. And it's a distribution that has this PDF. Okay. So this you can think of as the conditional expected value of y prime conditioned on x, little x. But now we have a new random variable, which is this y prime. Okay. And this y prime follows a normal distribution. However, that normal distribution does not have mean x transpose w star. It has mean x transpose w MLE, comma 1. Okay, so we've gone there. We still needed f bays. So what is this thing? What's the expected value of y prime? It's this, right? That's the definition of the expected. That is the expected value of a normal distribution. So we get that this thing is x transpose w MLE. Okay. But remember that w, whatever this w MLE, that's the same thing as this x hat that we've been seeing before all the time, which is the solution to the like linear regression problem with the squared loss, right? That's what this thing was. And so this would be our f hat that we end up using. So, okay. So where do we get to? We wanted f bays, and we got an estimate of f bays, which is f hat. This is the estimation part. This is the not exactly f bays part. And what our choice for f hat is exactly the same as what it was before. And so this is the like kind of coincidental, ironic part. We did a different method, which is to estimate the conditional PDF with this guy. And we got a different f hat. Okay. Or sorry, we didn't get a different f hat. We would think that we might get a different f hat, but we got the same one. Okay. So that's kind of cool that like you can think of like the thing we were doing before actually has some like other kind of grounding, which is that like maybe it really is quite a good option that we were doing before, because like if you try doing it a different way, which is through this maximum likelihood way, you end up with the same answer. Okay. There is some caveats though, which is that we made some assumptions right here, like which is that this is only true when you make this assumption that the conditional distribution of y given xi, this thing, is exactly this normal distribution with like an extra, with a variance assumption of 1. And if you change this, okay, well, if you change this, then it's the same thing as changing your function class for the predictors. So that's actually not that bad. Like if I were to change this thing to phi of I, like the polynomial features, you would get back the version of polynomial regression we were seeing before. So that's really beautiful. So this is not that limiting. So if you change this to like neural networks, then you would actually get the version of neural networks for like normal estimated loss version and everything like that. So that's not that restrictive. What is kind of restrictive is this variance being assumed to 1. If you don't assume it to be 1, then you really do get a different solution. Okay. And I don't quite remember what that solution looks like and what it relates to. And it's not that common to talk about. We're not going to talk about in this course. But I did want to mention you get something different. And there things don't. So things really line up in this special case. And there's another assumption that we didn't do, which is we didn't assume anything for this. Okay. And you could also assume something there, and that will change things as well. Okay, I think that's more or less all I wanted to say there. And maybe like the other thing is that you also kind of didn't make any. Okay, well, that's what the next thing is going to talk about. So maybe I don't say anything about that yet. Okay, so that's all I want to say about this maximum likelihood stuff. The next thing to cover is this thing called maximum a posteriori, or you can think of it as just like having some more knowledge about W. In the sense that you know kind of like what region, what values W might take. And we will talk about that next. But first, I answer some questions maybe. And there's only one question, which is, most of the distribution in real life is not normal. How will we solve according to that then? And the answer to this is that if maybe the thing that I mentioned is the strong assumption is that things are normal to begin with here. And this is not the case. So if you change this to like, okay, so if the distribution really maybe is like something else. So in the classification case, for like binary classification, where you classify either correct or not correct, or like true or false, that is actually follows exactly a Bernoulli distribution, which is what we saw here. And that's why I kind of left this thing here, because when we cover classification after reading week, what we're going to do is we're going to just, we can do this maximum likelihood stuff all over again with a Bernoulli. And there it's actually very clear that it's a Bernoulli. And so that makes sense. And you're going to find that what we solve there gives you like a different objective. So when we end up solving everything, we're going to get to here, and we're going to see that this thing looks quite different when we have a Bernoulli. And that will be that's actually how we're going to approach regression classification. We're going to approach classification from kind of the MLE version first, instead of doing the loss thing, because you'll see that it's actually not quite obvious what loss to use in classification. And I leave it at that, but we'll talk about that in classification. So you can change this to Bernoulli, but other distributions, like you have these Poisson and Laplace and things like this, you might think your data is coming from, or you just might not know at all. And if you don't know at all, then it's kind of hard to use maximum likelihood, actually. And so then our previous approach, where you just say, I want to minimize the loss, is kind of like a more universal way to do things, because there you don't need any assumptions on the distributions of things. You just say, okay, I need a loss that gives me that describes my goal, and like that actually describes the goal correctly, in the sense that I want my labels to be close to their predicted things. So as long as I have a loss that makes like when the loss is small, that means my labels are actually close to my predictions, and vice versa, then you have like a pretty okay loss, and you can use that. So yeah, in some sense, this is like a more restrictive way to do things. It is, in some sense, a little bit more foundational from the statistics world and stuff, and they really like this stuff. And then one other thing about this whole MLE stuff is that one other added benefit is that we've learned the whole conditional distribution. So we use the conditional distribution in here in the way that we calculated its expected value, but we know other information, which we also know like the variance and what it looks like and stuff. So in particular, when we did the old version of things, where we just learned a predictor, we only learned like this function, like for instance, this line, let's say, or something close to it. We would have just learned something like another line like this. That's hopefully close to the true thing. So maybe this thing's f base. This would have been our f hat in the old version. Now what we've learned is we also have learned, okay, I should probably change it another way around. I'll call this thing f base. And this thing f hat. And what we also learned is we also learned kind of what distribution we could expect for each x. So we could also like talk about other things, like, I don't know, the quartile of things and or the variance of things and stuff like that of our predictors based on for a fixed x. So it kind of gives us some further information, but you needed to make this extra assumption of normal distributions and stuff. Okay, and I answer one more question, which is, how did you get the X transpose weight MLE in the last few steps? And I guess it's this, and okay. Maybe good to clarify as well is that there was these couple steps that I got through here, and the story was this, that like the definition of an expected value looks like this. Okay, so what you do is we got to here. Hopefully this stuff should make sense. All I've done is replace this with an approximation or an estimation. And then I notice that this is exactly the definition of a conditional expected value. So I write the conditional expected value, and I say that if this y prime conditioned on x had this distribution, then this thing, this conditional expectation, would be equal to this. That's by the definition. And then if I have that, then I'm done, because like this conditional expectation has a mean, or it has it has a value, and it turns out that that value, since it's normally distributed, is exactly this. This is the expected value of a normal distribution. And so then I plug that in, and then we already saw that this MLE solution is exactly the previous solution we saw, and then we get that's f hat. Okay, so that hopefully clarifies things. And okay, so the next thing to cover is this maximum a posteriori thing. And I didn't prepare anything for this, but I think it's worth a couple minutes to just give like the high-level idea and the title in a new note, and then we can take it off from there, because it's very related to MLE. And what we're going to do is we're going to solve a very similar problem with like as before, but we're going to find that we get a new predictor, and the predictor, maybe I will ruin it, and you're going to find that that predictor is going to be somehow related to the regularized predictor. Okay. So what is this maximum a posteriori thing doing? So like it somehow comes from this MLE thing, is one way to think about it, which is that if you have further knowledge about your parameters W, in the sense that you know, okay, that like maybe you know that the slope, so how like this thing, like, you know, f base, you know, it's not like, you know that W is not like unbelievably, like it's not enormous, like the slope's not huge. You don't expect that like if you change the house price, or sorry, if you change the number of rooms like from 1 to 2, you don't expect the houses to move $10 million. Okay, so you know this, like at least this extreme. You also know it's probably not going to move 0. So you have like some information about W most of the time. And sometimes you can have even more information, which is like maybe it's also some distribution. And so so that's what map a posteriori, this map thing is going to do. It's going to say, what if we knew some further information about W and modeled it as W actually being a random variable with some distribution? And at this point, I might as well make the note. So the note is going to be this thing called map. Okay, that's the title. So it's called maximum, not likelihood, maximum. And I think it's spelled a posteriori. And if I spelled this wrong, I'll fix it for next time. Estimation. And they don't in the name. Okay, so that's called map. And the A and the P come from a posteriori, and estimation doesn't get included in this short form version for who knows what reason. And the idea is like, okay, so what if we had some, and this is the actual like mathematically correct word to use here, which is some prior knowledge about W, or like about, maybe I should put about the parameter. And like, okay, the parameter could be anything. Like for the Bernoulli case, it was that alpha thing. For the normal distribution, it was mu. In this case, where we assumed that the mean was like this linear thing, it was x times w. So I'm not going to write like the actual parameter, but like, yeah, depending on what distribution assumptions you make, you're going to have a different parameter. And if you have some prior knowledge about it, well, then like you can model it. Yeah. So if you have some prior knowledge about this thing, then you can use like what is like, you can have a prior on the parameter. So okay, maybe I'll write a parameter w here. And so then you can have this thing called a prior. So you'd have an actual, okay, you'd have like an actual distribution over w. And you'd have the corresponding like PDF or PMF over w, depending on what kind of a parameter it is, if it's discrete or continuous. And so this is called like your prior distribution. Okay. And what we will find, okay, I just write this and then we'll formulate this next time. But what you'll find is what this map thing is doing is we found that MLE was doing something like this. Maximum likelihood was the solution to the argmin, right? The argmin, let's say our parameter W from some parameter space, whatever it is. And it was maximizing the negative log likelihood. And the way you can write this is the negative log, and then I said one way to write the likelihood, instead of writing all these products, people will often write the joint PDF of the data set, given the parameter. Okay, so that's how that thing was written. Turns out that when the map thing, when you actually assume that this parameter has some distribution, then you're really assuming this parameter is a random variable. It has some like distribution and stuff, and you have some knowledge about it. So then you can actually, this notation actually starts making sense and stuff. And what map ends up, you can think of map doing is you can think of it as, well, we're going to see that it's exactly solving this problem, which is it's finding the parameter that no longer minimizes the log likelihood, but it's going to minimize this other thing, which is this joint PMF or PF, but it's actually going to be over the parameters W conditioned on the data set. Okay, and I maybe write one more thing for this interpretation of what this is, and then we ended there, which is you should really think of this thing as you can rewrite this using the product rule, and then, or like, I forgot, maybe it's Bayes' theorem or whatever and thing, but you can rewrite this guy as the following, I believe. Okay, maybe I don't write this because I can't quite remember what okay. Okay, maybe I don't. This is going to take a little bit longer. Okay, but anyways, the point is it's going to be related to MLE. It's actually going, you can rewrite this as this term multiplied by a prior, and that so then you can really think of this as like the MLE version, but scaled by some prior. Okay, so that's how I leave it. This map thing is going to somehow address prior knowledge on W. Okay, that's all I have to say for today. And we'll finish this map stuff on Tuesday, and then on Thursday we'll have the midterm review. So it's going to be, midterm is going to be based on everything, like including map is what the midterm content's on. No logistic regression, which is going to be covered after reading week. Okay, well, thank you everyone, and I shall stop recording now.